private college for around 2 years. So I joined in 2006, and the main mandate of NITTTR is, as the name implies, it's technical teachers training. So we conduct mainly training programs for the faculty of engineering colleges and polytechnics in both contact mode and ICT mode. ICT mode is more or less the one which we are doing right now. When we make the use of technology. So we have some ICT in the ICT courses. It's not an individual who is attending. It's like a college has become a remote center, and there's one local coordinator there, and a group of faculty from a particular college, they attend the course. So it's like that. And the other mode is contact mode, wherein as some of your participants, Mr. Ganesh Jadhav, as I can see, he was here, I think, for AICT course, and one or more participants. So they come to NITTTR Chandigarh and they attend the program face to face. So it's kind of 5 days program. Now, apart from these programs, we also conduct, as Sir has read my biodata. So I have conducted 2 ARPIT-based courses on Swayam platform, and I think this is the best time when Sir has told about it, because I'm going to rerun the ARPIT program. It was on big data analytics and smart grid. So just 2 days back only, we got an email from Ministry of Higher Education, Minister of Education, we would say now, MHRD. It's Ministry of Education, that because of the COVID situation, it will not be possible to run new programs this year. So we are going to rerun the ARPIT program. So for those who are interested in attending, so these are MOOCs courses. I think most of you are aware of what MOOCs and Swayam is. It's an initiative by MHRD government, and the courses are free. Of course, they are free, and it will be offline. It will be in offline mode. Like in this case, so we are having a live interaction. So in that particular course, it's on big data analytics for smart grid. Very, very nice course, I think, because in the coming time, when we are talking of smart grid, which I think this course which you are attending is also focusing on smart grid. So then big data analytics, it plays a very important role. So that is the course which we are going to rerun. And in fact, on 15th of November, we are going to upload the introductory video for that. And on 1st of December, the course is starting. So you can just register yourself for that ARPIT course on big data analytics for smart grid if you are interested in learning about how to apply machine learning, then your artificial intelligence in the area of smart grid. So that's about it. Apart from that, we also conduct courses on real-time simulation, because that's the topic which I'm going to cover today in the area of WECS, that is wind energy conversion system. But we also conduct courses mainly with industry. Recently, we have conducted 2 industry supported courses. So till December, all the courses are going to be only online mode only. So recently we had concluded a course with OPAL-RT. OPAL-RT is one of the industry which mainly deals with real-time simulation. That's what I'm going to tell you about, what real-time simulation is. That was on real-time simulation, a roadmap for renewable energy grid integration for smart grid. And apart from that, there was another course in the month of August, which was done in collaboration with Typhoon HIL, which is another very good industry which works in the area of real-time simulation. So apart from these courses, we also conduct power quality related course. Yes, in the month of December, from 5th to from 14th to 18th December, I'm going to conduct one course on power quality. And Panda sir, I'm definitely going to invite you as an expert there. So I'll take this opportunity.
Thank you. Sure, madam.
Yeah. So those who are interested in learning about the power quality issues in power converters, power electronics, so that course is going to happen from 14th to 18th of December. So you can start the registration. So this was all about my institution. And yeah, apart from conducting the courses, we also have MTech program in ME in electrical engineering with specialization in instrumentation and control. And we also have PhD programs. So in fact, we have a Center of Excellence with in a hardware in loop, in which we have an MOU with Typhoon HIL, which is a Switzerland-based company, and they are sponsoring one PhD candidate. Just 2 days back, we have interviewed one PhD candidate who will be sponsored by Typhoon HIL. So for some of you who are interested in carrying out your PhD work, you're most welcome. Till now, in the QIP, we have QIP with polytechnics. So mainly faculty from polytechnics who get sponsorship for QIP, they attend PhD here on the regular mode. But from the next year, it is going to be open for engineering colleges also. So in case you are interested, you're most welcome to do PhD in NITTTR. We have very good research facilities in the area of especially real-time simulation and hardware in loop and all those things. So if you get a chance to visit Chandigarh NITTTR, then you're most welcome. We would love to show you all around what all facilities do we have. Okay, so this was all about the idea.
Thank you, madam. Thank you, madam, for a brief idea about the NITTTR Chandigarh and the different facilities available at your institute. Definitely the participants will take the interest, and because we are in a same platform, means whenever we will get the opportunity, definitely we should take that advantage.
Oh, sure, sir, sure.
Okay, madam.
Oh, coming to my session today, let me just open my presentation. We'll keep the question answer session for the last 15 minutes. Okay. So in the meanwhile, you can just keep writing your questions in case you have in the chat box, but we'll have the question answer at the end of the session. Yes. So for around 1 hour, we'll have the lecture, and last 15 minutes we'll keep for question answers.
Yes, madam.
So are you able to see my screen?
Yes, madam.
Yeah.
Yeah, participants, is it possible? Can you respond?
Yeah.
Any of the participants?
Visible, ma'am. Can you just hide the pop-up button?
Yeah, that's what I was just about to do. I'm going to hide this thing.
Okay.
Yeah.
Yeah, it's visible now.
So my topic for today's lecture is real-time simulation of doubly fed induction generator-based wind energy conversion system. These are all the top topics which I'm going to cover. Firstly, I'll cover the need for wind energy, what are the basics of WECS, and then finally real-time simulation of DFIG-based WECS. I'll also show you what all facilities of DFIG do we have at NITTTR Chandigarh at the end of the session. Now we know that wind is considered to be the energy source of the future. We know why, because it is clean, abundant, and renewable. We know what is the need of renewable energy sources on the rise because of the energy crisis in the world today. This is well known to all of us. And when we talk about the clean wind energy, then you can judge from this fact that wind turbines can reduce the carbon dioxide output by around 125 million metric tons, which is equivalent to about 26.4 million cars. And also it reduces the fossil fuel emissions. And if we talk about the worldwide installed capacity of wind energy and the data that by December 2019, the total worldwide installed capacity of the wind energy was 651 gigawatt. Okay. Otherwise, thank you. So we have just made an alternate arrangement also in case this God forbid shuts down again.
Left side में लगेगा ये इसका mic का.
Okay.
Right वाला.
Thank you. So this was 651 gigawatt, and you can see from this table also that right from 1996 it was 6.1 gigawatt cumulative capacity to 2018 it has come up to 591, and as we just saw by December 2019 it was 651 gigawatt. And if we talk about the wind energy conversion system in India, then as on February 2020, the total installed capacity of wind in India was 37.669 gigawatt, while it is planned to produce 60 gigawatt wind power by the year 2022. And if we talk about the position of the India among the world, then it has 5th global position for overall installed capacity and 4th position for the wind power. Now you can see the block diagram of wind energy conversion system. The main components, as we can see, this is the wind turbine, which normally has 2 or 3 blades, and the kinetic energy of the wind is converted into the mechanical energy by the mechanism here, which is further converted into electrical energy with the use of this 3-phase generator. And of course, the control part is very important of the wind energy conversion system. And we also require some step-up transformers before the power is supplied to or taken from the supply grid. So this is the overall block diagram of a wind energy conversion system. Now, if we talk about the wind turbine technology, this diagram shows it, and let us just see one animation in which each part has been explained how wind turbine it works. So are you able to see this? Is the screen visible?
Yes, ma'am.
Okay. Actually, in case of team, firstly, I have to stop sharing and again sharing. So I was just asking. Okay, so this is how the wind turbine works. These are the various components. So as we can see, the blades which lift and rotate when the wind is blown over them, causing the rotor to spin. So as I told that most of the turbines, they have either 2 or the 3 blades. And then we have a rotor. Rotor means the blades and the hub. Together, they form the rotor. So please don't confuse this rotor with the rotor of your DFIG. That's separate. We are talking about this rotor. Then we have this pitch system. Pitch means which can turn. So pitch system is used to turn the blades out of the. It is used to turn the blades whenever your wind is blowing to control the rotor speed. It also keeps the rotor from turning in winds that are too high or too low to produce the electricity. And then we have this low speed shaft. The wind is capable of rotating this low speed shaft at about 30 to 60 RPM, which is not enough for our generator to work. So that's why we have this gearbox. This gearbox connects the low speed shaft of about 30 to 60 RPMs to the high speed shaft, and it converts it into 1000 to 1800 RPM. That is normally the rotational speed which is required by most of the generators to produce the electricity. Now, the gearbox is a costly affair, and nowadays a lot of research is going on that engineers are exploring if we can have a direct drive generators which can operate at lower RPM and which do not require this gearbox. Then we have this generator, of course, which is used to convert the mechanical energy into electrical energy. Finally, we have this high-speed shaft, as I said, which drives the generator. And this thing which you are seeing here, it is anemometer. It measures the wind speed. And this wind speed data is then sent to the controller. Now, why we require to send this data to the controller is because there is a concept of a cut-in speed and cut-out speed. Cut-in speed means the minimum speed, the wind speed which is required for the operation of the DFIG, which is around 3 meters per second and 3 to 6 meters per second. And cutout speed is the maximum speed after which the operation of your turbine, it should not be done because it may cause damages to your system. So it's around 25 meters per second. So that's why this data is sent to this controller, which further gives the signals whether to turn on the system or turn it off. Now, apart from all this whole setup, I mean this whole white thing which encloses all the setup is known as nacelle. So nacelle basically it sits atop the tower. So you have a tower and you have this nacelle which contains all the shafts, the gearbox, the generators, controllers, etc. And this is the yaw motor. Yaw motor basically means which is used to drive the yaw drive. Now, what is the purpose of this yaw drive? So you see, you have 2 types of turbines. One is known as upwind turbine. The second is known as downwind turbine. Now, upwind turbine basically needs, as the name also implies, needs to be faced directly to the wind in order to operate. So that's why this yaw drive, it orients the upwind turbine to keep them facing the wind whenever the direction of the wind changes. Whereas the downwind turbine, they do not require a yaw drive because they automatically, the wind manually blows the rotor away from it. So this is all about the wind turbine and how it works, because this is, wind turbine is a very important part of your wind turbine is very important part of your DFIG based wind energy conversion system. Now, this is another very important thing which is known as power curve. So, as you can see, this shows the relationship of the wind speed to the power generation. So, as I was telling you, this is a cut-in speed before which there is no power output, and after this only, as the speed increases, your power increases and it reaches to a level. So depends upon the specifications or the rating. Sometimes it's 12 to 14 to 16. So in between that range, meters per second, the speed of the wind, you get the rated output power. So this point is the rated output speed, and you get the rated output power. And finally, this is the cutout speed, as in this case, it's 25 meters per second. So beyond this, there should be no power, because the wind, if the turbine, if it is operated beyond the speed, it will cause mechanical stresses and thus damages. Then apart from this, there are other necessary components like foundations, power collection, substations, control, communication system, etc., which are there. And if we talk about India's 2019 wind turbine supplier market share, then you can see from here that Siemens is a topmost, and then you have Suzlon. Then you also have Vestas, Inox Wind, GE. GE is also a part of it, Envision, Senvion. So these are the major wind turbine suppliers in India, which are having the major market share. Now again, coming back to the block diagram of wind energy conversion system, we have seen the wind turbine. The next one is the three-phase generator. Three-phase generator, these are also very important part. So you have different types of generators which have been used in the wind system over the years. So these generators, they can be either synchronous generator or they can be asynchronous generator. So in case of your synchronous generator, you have PMSG. PMSG is permanent magnet synchronous generator, and also you have wound rotor synchronous generator. And in the asynchronous generators, you have squirrel cage induction generator, and also you have DFIG. And the most widely used among all the generators are the PMSG, that is permanent magnet synchronous generator, and your DFIG. I'll just this. Now, if we talk about the wind energy generator configuration, you have various types of turbines, which are mainly fixed speed turbines and the variable speed turbines. Now, the fixed speed turbines are, as the name also imply, these are the ones which operate at constant speed. Fixed speed means irrespective of the speed of the wind, they will always operate at a fixed speed. And in fixed speed wind turbine system, the rotor speed is constant. Okay, so the efficiency of such kind of turbines is quite low, because whether the wind is blowing at low speed or it is blowing at high speed, the rotor speed will be constant. So normally these fixed speed turbines, they are furnished with SCIG, squirrel cage induction generator. However, they, as I said, that they have quite a large number of disadvantages, because they have low efficiency, though they do not support the speed control, etc., and low power factor. So normally these days, the ones which are more popular are the variable speed wind turbines, due to the increased energy production. So as the name implies, that these are with the varying wind speed conditions, the power output of these wind speed, it changes. And of course, with the advent of the advanced power electronic converters, when they are interfaced with these turbines and DFI and your wind energy conversion system, so they play an important role in the variable speed operation. So among them also we have indirect drive, we have direct drive. Direct drive, as I told you, these are the gearless ones which do not require, which operate at low low wind speed, and these are the indirect drive. So among them, the most popular one is the DFIG one, which is most favored by the wind turbine industry. We can say that because of its various advantages, which we will see in the coming slides. Now, as we were talking about the advantages of variable speed turbine.
Excuse me, ma'am.
Yes.
Yeah, can I just interrupt for 1 minute? Actually, some of the participants are requesting that they are not able to see the PPT.
They're not able to see the PPT?
There are many participants who are, but I can see it. I don't know why the problem is there for the participants, because in between while you are presenting, one of the participants suddenly started presenting himself.
Okay.
Mr. Rakesh something. So can you just stop sharing and just can you again share it, ma'am?
Sure. Is it visible now?
Yeah, now it's visible, ma'am. Okay. Yes. Thank you, ma'am.
So we were talking about the advantages of the variable speed turbine. So as I said that because as the wind speed changes, these have control over that in variable power output. So sometimes you have a gust of wind. There's a term called gusting. So the power wind curve which we just saw beyond the cutout speed, that particular term is known as gusting. So sometimes what happens is that you have high speed winds which allow to make the rotor turn faster. So in such cases, what we can do is we can store the part of the excess energy as rotational energy until the gust is over. So this feature is not available in the constant speed turbine. Then also it's possible to reduce the peak torque, and we may also reduce the fatigue loads on the tower and rotor blades. And as I told you that with the advent of the power electronics, it's possible to control the reactive power. So which is not possible in case of your fixed speed turbine. So in this case, we have option to improve the power quality in the electrical grid, because this is another very important. I think this topic is being covered. I was just seeing your timetable. The power quality issues in your renewable energy sources. So with the help of so these power quality improvement is possible in case of variable speed turbine, is not possible in case of constant speed turbine. Now coming to the DFIG, that is doubly fed induction generator based wind energy conversion system. So as I said that it is the most popular one and is most popular in the wind turbine industry, and is known as the current workhorse, in fact we can say. So instead of the usual field winding which is fed with DC and an armature winding where the generated electricity comes out, there are two three-phase winding. One stationary, which we call as stator, and one rotating, which we call as rotor, and both are separately connected to equipment outside the generator. So that is why it is known as doubly fed induction generator. So you have the option of having the power both from the stator as well as the rotor. So that's why the term doubly fed is used. Now, what happens in case of a DFIG? One of the winding is directly connected to the output, and this is nothing but the stator. The stator of the DFIG is directly connected to the output, means your grid, and it produces three-phase AC power at the desired grid frequency. The other winding, which is nothing but the rotor, it is connected to the three-phase AC power at variable frequency. So you can vary the frequency of the rotor in this case, and thus you can change the power output also. So this input power is adjusted in frequency and phase to compensate for the changes in the speed of the turbine. And adjusting the frequency and phase requires an AC to DC to AC converter, power electronic. Normally, in short form, we call it PEC. In many books, you will be reading the term PEC. So that is nothing but power electronic converter. So using very large IGBT semiconductors, we use them, and it is bidirectional in nature, and thus it is possible to pass the power in both the direction by using this bidirectional converter. Now, coming to the principle of operation of DFIG, as I told you that you have, if you see this diagram, then this is your rotor of the wind turbine. So you have this wind coming, the kinetic energy is converted into mechanical energy with the help of this rotor, and then you have this gearbox which increases RPM, and then this mechanical energy is converted into electrical energy with this generator, and inside this you have the rotor, which is connected with the help of this power electronic converter to the grid. So the rotor is connected through this power electronic converter to the grid, whereas the stator is directly connected to the grid. And what happens is that another advantage, let me see if I'll show you later. So another advantage of using, another advantage of having this DFIG is that its cost is lesser as compared to the other variable speed turbines. How? Because in this case, your rotor, it is supplying about 1/3 of the power to the grid, whereas rest of the power is being fed directly by the stator. So your rotor is supplying 1/3 of the power, whereas rest of the power is being fed by this stator. So when you have this rotor supplying 1/3 of the power, then automatically the rating of this converter and of course the cost of this converter is 1/3. However, this option is not possible. This is not present in the other variable speed turbines which are not having DFIG. So let us now understand this principle of operation. As you can see from here, so this is your induction DFIG. So see, this is the mechanical power which is coming, and then you have one PS, which is nothing but the stator power, and then you have one PR, which is nothing but your rotor power. So, and you have one controller. So if you remember the block diagram of the DFIG based system, we saw that there was one controller. It's very important. So you can have 3 types of controls which are possible in this case. As you can see, one is this pitch angle. This is controlling the pitch angle of this turbine, rotor turbine. Then there can be 2 other controls. Now coming to this part, coming to here, you can see that this is a bidirectional converter I was talking of, the power electronic converter. So this is AC to DC and DC to AC, and in between you have this DC voltage capacitor, which is providing the, which is acting as a source of the DC voltage. Now, what is happening is the converter which is connected to the rotor is known as rotor side converter, and the converter which is connected to the grid is known as grid side converter. So you can have, again, apart from this pitch angle control, see, there can be other controls also. Of course, when we talk of WCS, you have your tip speed ratio, you can control that. Then you can control CP, is a coefficient, because it's very vast. I'm not going into those aspects. Right now, we are mainly talking about the DFIG part, which is the electrical part. There, these controls are possible. So as you can see from here, there are 2 types of controls which are possible. One is the grid side control, one is the rotor side control, wherein you control this part which is connected to the rotor. The other is the grid side control. Now, one important thing to understand here is that this rotor side converter, or the control which we are doing, it basically controls the flow of active and reactive power. Okay, the rotor side converter is able to control the active and reactive power. However, this grid side control, it's mainly done to keep this DC voltage constant, and sometimes it is also done to independently generate the reactive power towards the grid. Now, before coming to the control, let me just explain this. What are these terms written here? So there are 2 things. the two ways by which this can operate. One is known as supersynchronous speed. The other is known as subsynchronous speed. Let me just write here. So when I'm talking of the super synchronous speed, so what is happening? See. Okay, there is another derivation. I'll not go much into detail of that, but just remember this equation, that your PR, which is nothing but the power output of the rotor, electrical power output of the rotor, this is equal to minus S multiplied by PS, which is nothing but the power of the stator, electrical power of the stator. Now from this equation, if you understand this equation, it's very important. You see, the power, rotor power, it mainly depends upon the angle, it mainly depends upon the sign of the slip. Now, what is slip? We know that slip is nothing but omega s minus omega r divided by omega s, where omega s is nothing but the synchronous speed minus rotor speed divided by omega s. Okay, now let us now understand this thing. Now, the first case when I'm talking of the supersynchronous speed, in case of supersynchronous speed, this is the scenario wherein the wind is blowing at when the speed is higher than the rated wind speed. That means beyond your, if you remember that power angle curve, that means beyond your rated speed, it is that speed I'm talking of. So when your rotors, when your wind speed is blowing more than the rated wind speed, what will happen? Your omega r will be greater than omega s. So this is this scenario. So in that case, your omega r will be greater than omega s. So that means your slip is negative. So when your slip is negative, that means this is negative already. This is also negative. So that means your PR is positive. So in this case, the PR is transmitted towards. So this will be the direction of PR. So PR will be transmitted from the rotor towards your DC link voltage, and it will tend to increase your DC voltage. And in the second scenario, which is known as the subsynchronous speed, this is the speed wherein your speed is lesser than the rated wind speed. So in this case, which is scenario is this. So this is the scenario of omega r is less than omega. So if this is less than this, that means your slip is positive. Now in this case, slip is positive. So if this is positive, so automatically that means PR is negative. PR is negative. So this means, what is the direction of the flow of PR in this case? It is in this direction. So here your active power will flow from here to the rotor, and thus it will tend to decrease the DC voltage. However, our aim is to keep this constant. So what keeps this constant? Normally this converter, the grid side converter. So this bidirectional power flow of the rotor. So this is another one of the important characteristics of the DFIG. So all the advantages of the variable speed turbines, they are the advantages of the DFIG itself. we know that we are able to both import and export the reactive power, and of course when we are able to control this, then it has important consequences for the power system stability. So even during the severe voltage disturbances, your system is stable. Of course, we have seen whatever are the advantages of the variable speed turbine, they are the advantages of DFIG because it is operated in that. And of course, this is the factor which I was telling you, the cost of converter is low. Why? Because one third of the power is being fed by the rotor, and the rest is being fed to the grid directly from the stator. So that's why your rating of the converter will be low, and thus the cost will also be low. I'll just quickly come to the real-time simulation part now. So this is another block diagram of your DFIG based wind energy conversion system. So as we can see from here, you have both direction flow of the power in this case. And this is the control system which controls, one is rotor side control, one is grid side control. Then there is also this tip speed ratio control of the wind turbine. Now coming to the real-time simulation part of the DFIG. Firstly, we need to understand what is the need for the real-time simulation. You see, in response to the increasing demand of the electrical systems for performance, reliability, and cost, the control and protection equipment have become increasingly sophisticated. So what we do is that it's very important to validate these equipment before they are installed on the real power system. Right, the cost is increasing, of course. So before they are installed in the real power system, it is very important to validate these equipment. So to accelerate the development and validation cycle of these equipments to reduce the cost and risk, which we will see in the next coming slides, the current trend is to test these equipments with a real-time digital simulator. Now, what are my simulation goals? Why do we need to go towards simulation? One thing is I want to reduce the delay. I want to reduce the risk. Of course, I want to reduce the cost. Now, how? There is no need for a real-time, there is no need for a real system or a prototype. So what you will be doing is you will be making your model in the laptop. You will be dumping into your real-time simulator, and then you will be validating your system. So it is easier to detect the faults earlier. Of course, minimize the malfunctions after installation, reduces the delay because you are independently developing the hardware and software of the controller. So you don't have to wait, okay, that firstly let me develop the hardware, then I will develop the software, and then I will implement it and validate it. So these are independently being done and tested in the lab with your simulated environment. And of course, risk. As I said, that when you're talking of power system, all your equipments, they are becoming sophisticated, they are becoming costly. So again, you can't directly put them onto the system. It's better to have a better test coverage before actually implementing them into the your system. Now, the concept of real-time simulation, this is one of the misconception in the mind of the people. Many times they think that when we talk of real-time simulation, it means it makes the whole system fast. No, it doesn't make it fast. Please understand this concept first of all, because many people think that okay, it's real-time simulation means my work will become my whole simulation will become fast. No, as the name implies, it is your real time. Whatever results you would have got in the real time, you are getting them now, because your simulator hardware, its clock is synchronized with your wall clock or your wristwatch. Now let us see how. Now, suppose you have very large complex model. Many of you are researchers who must be working on some simulation tools like MATLAB Simulink or some other ones. You must be facing this problem that suppose you have a very complex and large model, then what happens is that your simulation takes a lot of time to execute as compared to what it would have taken if it was in a real system. However, in case of a real-time simulation, irrespective of the complexity or the size of your model, your real-time simulation will give you the results exactly at the same time with which the real clock gives you. I mean, if you have said that at t is equal to 10 seconds, my fault should occur for 4 cycles, then it will give you the results in that particular time. So this is the real-time simulation. However, if we talk about simple small models, again, if it's a desktop simulation, what do you mean by desktop simulation? Means the simulation which you are doing in your PC or your laptop, then they will be much earlier as compared to the real clock. But however, in the case of a real-time simulation, it doesn't happen. It will give you the results at exactly the same time. So how do we go about the real-time simulation? As you can see this picture, firstly, you design your model in Simulink. Okay, you design your model in Simulink, you make it compatible with the simulator. So the simulator which I'm showing you here is the real-time simulator by OpenRT, which is one of the very good company for real-time simulators. So you make your model, Simulink model, compatible with OpenRT real-time simulator, and then either you can see the results there itself, or else you can take out the results and see them on some CRO or oscilloscope, or else you can also execute those results on some hardware, and then again you can take these results back to your model. So this whole system, this is how the real-time simulation works, and this concept is known as hardware in the loop. Now there are basically three types of, when we talk of real-time simulations, there are three concepts. The first concept is known as model in the loop. So it's the preliminary design phase. What does it mean? In this case, both, see, when we are talking of a system, a power system or a microgrid or a smart grid, then you are having two things. One thing is you are having a controller. One thing is you are having a plant. For example, in this case, if you have a motor or you have a wind turbine or you have a solar system, so this is the plant, and one you have a controller. So in the model in the loop, both your controller and your plant are simulated. You don't have a real controller or you don't have a real plant. So both of them are simulated on the PC itself, and you just execute that on the real-time hardware. You don't take out the results, you don't actually implement it on some hardware or something. So this is known as model in the loop, and this is just a proof of concept. However, there is another concept which is known as rapid control prototyping, or the short form we call it RCP. So in this case, you have a simulated controller. Your controller is not real. So the example which I'm going to show you today will be this RCP only, but you have a real plant. You may have an actual motor, you may have an actual wind emulator or a wind turbine, you may have an actual solar, which is a real plant. But your simulator is simulated. It is just simulated in your PC. So what you do, you simulate it here, then you dump it into the real-time simulator. You get the results out from this real-time simulator and you give it to the plant. And the plant, you actually fool it. You make it into believe that, okay, there is an actual controller which is controlling me. However, there is no real controller. So this is known as rapid control prototyping. Now there is some other concept in which your controller is real. You have an actual controller, but your plant is simulated. It's the reverse. So in this case, you have a plant, you simulate it. Suppose you have a very big grid model. Okay, you don't have an actual grid, but you make a model. Let's say 3 machine 9 bus system. So you model it in the PC. You make a Simulink model. Then you dump it into the hardware, and then from there you take the signals and you make the controller. In this case, you are fooling the controller. You are making this controller believe that, okay, there is a real plant to whom I'm giving the control signal. So these are the three concepts. One is a model in the loop in which your both plant and the controller are in the PC, whereas the second was the rapid control prototyping in which you had a real plant, whereas the controller was simulated. And the third is real-time simulator. Your simulated plant is in the simulated environment, whereas you have a real control. And this concept is known as HIL, hardware in the loop. So it can be like this, as you are seeing, rapid control prototyping. You have a real plant. However, the controller you are having in the your simulator. Where in this case, you have an actual controller. This is a controller, whereas your plant is simulated. There is another concept also which is known as power hardware in loop, in which power amplifier is used and all those things. So these are the functional configurations. So I'll just quickly go through this. So how does it work? You have a host PC. in which your simulation is there, and this is a real-time simulator, and both of them are connected through the Ethernet. So this is a link between your host PC and the simulator. And in the simulator, you have multiple core CPUs in which your computation work is done. So the burden of your computation is taken from the host PC to the real-time simulator. Apart from these multiple core CPUs, you also have some FPGAs and input-output boards. So FPGAs are mainly used in those conditions wherein you have very high fast switching, like in microgrid model, wherein you have converters and all. So there you require very fast switching. So there FPGA is used. Also FPGA is used in case you want to take out the signals to some real, let's say a relay. You want to operate a relay using the signal. There also FPGA is done. Otherwise, the computation is mainly done in case of your multiple core CPU. So these configurations which I'm telling you are basically of OpenRT. I'm telling. OpenRT. It may depend upon different simulator by different companies, but this one I'm telling wherein you have multiple core CPU and FPGA and all. So this is in the company OpenRT. So this is the same as I told you. This is the host PC. This is the target PC. So you have just built your model here through the TCP/IP. You are connecting it to the simulator, and through the simulator you can either see the results on the CRO or you can see the results on this. You can give it to some relay or some output. Yeah. Now what happens is that whenever you make the model, what you do is you make subsystems. You make two subsystems. One subsystem is of your master subsystem in which all your computational models, your algorithms, physical models, they are basically grouped into that subsystem. The second subsystem is your graphical interface in which your scope or whatever results you want to see. So your graphical interface portion, it is basically executed in your host PC itself. However, the rest of the system is executed in the real-time target. That means the complex model is executed on your CPU, whereas the graphical interface is executed in your host PC. So that's what I was saying. You group it into subsystems. One is known as the master subsystem. One is known as the console subsystem. So this is how, I mean, this is a separate topic of how the real-time simulation works and all those things and how is it executed. But I just want to give you an idea about what is the meaning of real-time simulation. Why do we need to go towards real-time simulation? And of course, how is the real-time simulation executed? Now, the real-time simulator, which is there in the electrical engineering department of NITTTR, it is the RT Lab digital simulator developed by OpenRT Technologies, which is a company based in Montreal, Canada, and they have their office here in India, in Bangalore. And this is the real-time simulator OP4510. They have various different simulators models we have. Apart from this OP4510, last year we also purchased their upper model, which was OP5600, which has been connected with PMUs and VAM system. And apart from that, we have this OP8662. This is a signal conditioning module. So basically your input and output. So it has got your sensors, current sensor, voltage sensors, which are required. So that setup is OP8662. And of course, we have one DFIG setup with the control panel. We have 6 kilowatt DFIG setup here at NITTTR. So this is the picture of our system which we are having. So this is a OP4510 OpenRT real-time simulator, and this is a DFIG control panel. In this you have rotor side converter, grid side converter, etc., all the control, and this is the DFIG, and this is OP8662 voltage conditioning block, wherein you have voltage signals and current signals. You can just take from here and then give it to here and then accordingly. So let me just show you how the DFIG based wind energy conversion system is executed using OpenRT. This is a quick video.
Excuse me, madam. Audio we are not getting.
Are you not able to hear what he is saying?
No,
Audio
no,
is
no,
not-
madam. No,
Okay.
only video. Just we are picture we are
Okay,
getting,
okay.
but no audio.
You just see the video first. I'll explain to you. I'll just steal the video and then I'll explain what all he told.
Okay, okay, madam.
You just see the various parts which he's explaining. I'll explain. Okay, let me just put this aside. Okay. So let me just show you what all it is there. So in this case, this is OP8662, wherein you take out the current signals and the voltage signals. And this part, this is a different setup, although this is not the one which we are having at NITTTR. However, it is the same. I mean, the concept is the same. So we also have this OP8662, and this part is basically the controller of the inverters. So one side is the rotor side rotor side converter, the other side is the grid side converter. So here in this case, this is their real-time simulator. So what is happening is that we have one actual DFIG emulator. Okay, so DFIG emulator is there, which is actually imitating a wind turbine, and by varying the speed of that what do you call it, induction generator. So by varying that, it is actually imitating the wind turbine variable speed. Now what is happening is that you have a plant here. You have a real plant. Okay, why real plant I'm saying is because your dynamometer, or we can say the wind turbine emulator, it is basically working, or it is imitating as a real wind turbine, and your controller in this case is virtual. How we can say? Because your controller is there inside the simulator. So what you have done is control algorithm you have developed and into a Simulink. You have not actually developed the controller, but you have developed a Simulink model of the controller. It may be vector control or any other control, but you have dumped that or burned that into this real-time simulator. So that controller is sitting here. And this controller is sending the firing pulses to your rotor side converter and your grid side controller, and all the signals feedback, they are coming through this. The voltages and the currents, they are coming from here. So this is how it is happening, and this is the graphical form which they have represented in their PC. Actually, they've made use of LabVIEW. LabVIEW is also compatible with RTLab. So just in order to show you how show you the graphs and all those things. So in this case, this part is the rotor side converter, and this part is the grid side converter, and in between you have this constant voltage. So all these waveforms and all, they were just showing the DC link voltage, the active power, reactive power, how this is the this was the panel for the variation in the wind speed. I mean, when they turned on your DFIG, the wind emulator, how the wind speed, it reached at a certain level depending upon your algorithm, it reached the rated speed. Then suppose you when you turn on your this thing, pulses, how the pulses are. Now in this case, the pulses are actually coming to these inverters. However, your controller is not fabricated. Your controller is not actually there. You have just made a Simulink model, but with the help of this real-time simulator, you are taking those signals which would have been, अगर आपके पास वो actual में होता, अगर आपके पास एक्चुअल में एक कंट्रोलर होता जिसको आपने which you would have fabricated, and you would have got the signals which would have given to these converters. So this is the whole setup in which your DFIG based wind energy conversion system using OpenRT. So this concept is the concept of rapid control prototyping, which I was telling you, in which your plant is real. You have a real plant, you have an actual motor which is acting like a wind emulator, but your controller is simulated. And then by taking the real signals, taking actual signals, you are you're controlling, you're giving pulses to the rotor side inverter or grid side inverter, whichever control you want to take. So in today's session, what all we have done is we have seen that what is the scenario of the wind energy, then what are the various types of wind turbines, and then DFIG, what is the advantage of DFIG, how it is used, and then finally we also saw real-time simulation, the concept of real-time simulation, and why it is required, how we can implement it, and then finally I showed you one example or a demo in which by using OPEL-RT, DFIG based wind energy conversion system was used, in which your simulator or in which your controller was not real. It was their simulated environment, however your plant was real, and you were actually taking out the signals and feeding them into your converter. So this is all from my side.
Thank you, madam. Thank you very much, madam, for a brief presentation on the wind energy system, and particularly the real-time simulator, all those facilities available in the NITTR Chandigarh. Hopefully all the participants will be getting that exposure, and whenever they want to do any kind of research work, or they want that kind of platform, they can also take the help of you. If it is possible at NITTR, they can test their controls algorithm also. That is a nice presentation, and hopefully all the participants have already got this facility. Many of the institutes having that OPEL-RT, but if you'll see, most of the NITs also don't have that OPEL-RT facility. Because what kind of facility we are using, that is not important. Important is that how the research is going on with the control algorithm, how it is tested. That is much more important. Then if the OPEL-RT is there, then it is very useful, and we can test our control algorithm. That the madam has already briefed in details.
Actually, sir, this time was really short because I had to tell you about DFIG also, then I had to tell about real-time simulation also, and how we can just incorporate both of them and
Yes.
all this. Because DFIG is a very vast concept. If I start the control algorithm itself, it is not possible to cover that in
that is true. That is true, madam. That will become another FDP.
FDP, yes.
Wind energy conversion system.
Very true.
That will be another 5 days FDP will be there.
So one of my PhD student, he is working on this DFIG based system only. He is developing one FOPID controller. So he will be simulating that in OPEL-RT, and he will be implementing it on the DFIG.
Okay, fine.
He's already doing such work. In case you people are interested,
we'll be taking, madam, only 1 or 2 questions if any doubt is there from the participants. Kavila, any question is there?
Yes, sir. I can see some of the participants are asking about the real-time simulator. I request the participants to unmute and ask, because I cannot understand the question exactly.
Yes, better.
What they are asking.
What is his view? Let him to ask directly.
Madam, for a 2-core simulator, is it possible to
you introduce yourself?
Myself,
I'm requesting you to introduce.
Myself, Vibhuti Prasad Sahu, Assistant Professor in BSSUT Burla, Odisha, in Triple E Department. Madam, that if the OPEL-RT that it is a 2-core, then is it possible that one of the core can you use for the hardware in loop simulation? Because I have used for the model in simulation for that first type of. But that in our institute that is having 2 cores, so can it possible that I can use 1 core for the modeling simulation and another core for the external hardware type of things? Is it possible?
Yeah, that's a very good question. In fact, whenever you make your model in the Simulink, and when you make it compatible with your real-time simulator, as I told you, you have to take some subsystem. So one is a master subsystem, one is the slave, one is your console subsystem. Sometimes if your model is complex, you may require a slave subsystem also. So, but if your model is not very complex, then one CPU core is enough. One of the CPU core is enough. It all depends upon the complexity of your system, of the model which you are making. Suppose it's a very big system, very high number of buses you are taking, then your one core not be enough. Then you have to see the computational abilities of one CPU core as compared to your it depends upon your model, because many of our ME students, they have developed models, they were using only a single core. Till last year, we had only one single core which was activated. Then later on, we purchased more activations. Yes, it is possible.
Okay, okay. Thank you.
Thank you. Any other question from
Hello.
anybody?
Hello.
Yes.
This is Ganesh Zadav from Kekewa College of Institute, Nashik, Maharashtra.
Yeah. How are you, Mr. Ganesh? I think you came
Fine.
to
Yeah.
NITTTR for a course, na?
Yes, yes. I did the course which you have conducted under the IICTE. I was there for 5 days, and I have physically seen that your OPLRT setup there. Okay, so one thing which I want to ask that when you are using this simulator, is it the parametric variations and its effects is in the transient mode? Is it visible for in the OPLRT or any real-time simulator? Suppose that we did a parametric variation and its effect on the output that is easily visible on this real-time simulator. What is the sampling of that output and all the things?
Okay. Yeah, it depends upon, suppose you are working on power system, your sampling will be 50 microseconds. Suppose you are using very fast switching, in that case, your sampling rate will be in nanoseconds. So if you're talking about the sampling time you are talking of.
Madam, his question is like this: if any transient occurs, whether any changes will be in the current waveform, voltage waveform, like that. His question is like that. If you create a disturbance at a particular time, whether immediately there will be a response in the current.
Immediately it will be response. Exactly, immediate. When I say immediate, it means suppose you are running a simulation and you have said that okay, at t is equal to 10 seconds, a fault should occur. Then it will occur after 10 seconds, not immediately. That is what I said, that real-time simulation doesn't mean fast. It means at the same time. Irrespective of your model is very simple, irrespective of your model is very complex. It will give you the results at the time you have specified.
Okay, thank you, madam.
Thank you, ma'am. Thank you, ma'am.
Time simulation, I would say, because when you are testing your system, it has to be in real time. Means how the system will behave if the fault was to occur at this particular time. I have to give a signal to the relay at this time. It will give at that time. The results are visible at that time.
Okay, thank you, madam. It's okay if there is no question, and we'll conclude this session now.
Sir, may I raise a question, please?
Yes, please introduce yourself.
Hi, sir, it is Nidhi Saujani, and I'm a lecturer at Government Polytechnic Rajkot, Gujarat. Ma'am, I would like to ask, actually I'm working at distribution level, 11 kV. So when small scale distributed generation...
PhD? Are you pursuing PhD in that particular area?
Yes, sir, yes. So I would like to work on fuse and relay coordination, because when such distributed generation are integrated, they will feed current in case of fault. Of course, the fault current will be very minor, but it will affect the coordination between fuse and relay. So I want to know, is it possible that I can work on this simulator which you have at your institute?
See, the simulator doesn't discriminate whether you work on power electronics, you work on power system, or you work on any other. If you are able to make your model in Simulink, because you should be able to make your model in Simulink, it should be, then you can make it compatible with RTLab, and then you can see the results. So it depends upon if you are able to make your model in Simulink, whatever results you are seeing there, it's like you see the same through simulator itself.
Okay, so I'm actually wondering for my validation. So I will make a model in my Simulink, and is it possible that I can validate over there at your institute with your simulator?
You have to take the permission. Definitely, there will be some formalities will be there, I think.
Sir is right.
Okay.
Because, you know, these are very costly equipment, so we just cannot allow anybody to do the results and all. In case you have some collaboration with NITTTR
Yes.
in some way, then it
Yes,
is.
yes.
But otherwise it's not.
Okay.
Means
Thank you.
you have
Thank you,
to
ma'am.
consult, but there is a way to find out, but you have to think of it.
Mhm. But simulation must be in Simulink. That is the
Definitely won't be
condition.
available.
Yes, it
Yeah,
has.
but
Okay. Okay, ma'am. Thank you.
thank you. Thank you. Any other queries from anyone wants to know something? Okay, madam. If there is no question, thank you for your valuable lecture, and hopefully in future collaboration also will take your help.
Definitely, sir.
Thank you.
Thank you.
Thank you.
Thank you
Thank
to
you,
all the participants. Please